All right, so let's go ahead and get started. Welcome to CS24. I'm Donnie. I'm sure all of you already know me pretty well. This class is Introduction to Computing Systems. Very well-known, popular class, as you can probably tell from the room. This, is, like I was saying, is the highest enrollment we've ever had, tied with last year. I suspect that we'll probably exceed it a little bit, but I mean, it just sort of goes to speak to the popularity of the CS major and the CS minor, and hopefully to some small extent the material in this class, which I personally really love. I think it's really a fascinating topic. These are the kinds of things that we talk about in this class. How do modern digital computers work, where modern is defined as probably 1950s forward, which is more or less modern than some of us here in this room, but certainly very recent development. Features, capabilities, optimizations that processors provide. How do we translate programs to run on processors? You'll get a lot of experience with that in the first few weeks. How do we provide common runtime support? And this sounds really advanced, but it's actually quite basic. Things like subroutines in dynamic memory management and facilities like that. And what do operating systems do? All of you have computers that you use. You're probably using some right now. And they have operating systems and they provide certain facilities. So we spend some time talking about that toward the end of this class as well. So pretty broad, nice introduction. I wouldn't say it's a gentle introduction. Nobody would say this is a gentle introduction, but it's definitely a good overview of all of these kinds of topics. Now, there is a course website, and you need to sign up on it as soon as you possibly can. If you are already bored, you should do it now. You can go to the Caltech Moodle and find CS24. I believe that I have successfully set the enrollment key to be ALU, all lowercase. And if it's not that, then it's still Pinkston. You know how they always set up the instructor's last name for the enrollment key until they change it. So please do that quickly, because I send all course announcements that way. I put the policies up on Moodle. That's where lectures and assignments get posted, and that's where you'll submit your homework submission. So this uses your IMSS username and password if you're not sure about that. Okay? Yeah, so I already talked about that. Oh, I do want to mention the parenthesized statement. I will keep track of your overall grades separately. Moodle is not very clever when it comes to managing grades, and since some assignments are weighted differently than others, exams specifically, and because we also have a bonus for filling out feedback surveys, and there's a late penalty for lateness, Moodle's not very clever at doing all that, so we keep track of grades separately. If you ever have any questions about your grades, feel free to ask either myself or a TA, because we'll be happy to share that information with you. Also, like I say here, there will be grading guidelines posted, general ones. Programming is really kind of a frustrating and different thing, where the quality of your style and the maintainability of your code is very, very important, and so we do factor that into your grading. If you want to have good scores, then make sure you comment your code clearly, make sure it's well structured, make sure that, unfortunately college is a bit of an artificial construct. You don't have to maintain code that you wrote a year and a half later when you're in college. Okay? You get to throw it in the bin and move on. And so we will be grading you, though. That's the way that we can sort of teach you these things as if that were the case. So you'll get plenty of feedback on that. I'm sure that everybody will figure that out very quickly. We see that every year. Okay. Let's see. This is the approximate course weighting. Now, I don't know why I say approximately this is the course weighting, because it's always the course weighting. So, but midterm and final exam are each worth 15% of your grade, and there's 8 assignments that are worth the other 70%. Okay, so you can do the math. It's not hard to figure this out. Okay. I will rarely curve assignments. Now, this is so rare that you should expect that it won't happen. That's a nice default assumption, unless I do something horrible on an exam, designing an exam. So, typically, the averages on assignments are anywhere from 80 to 95%, seriously. And, my classes, everybody sort of says the same thing. Donnie's classes are hard, but it's just in the amount of work you have to do. If you get all the work done, you'll probably do really well. In fact, I think that 70 to 80% of my classes in CS24 end up getting a B or better. Okay, so do the work, learn a lot, and get a decent grade at the end. So that's not too bad. Late assignments are penalized. We do this mainly so that we can keep everything chugging along at a decent rate as far as getting things graded and so forth. I am hiring 1 metric crap ton worth of TAs, so we should have plenty of people to help, especially with this large of a class. So that should help a lot. And so that's the reason for the late penalties. You'll notice 1 day late isn't a big deal. You can turn in an assignment or 2 a day late and still get an A in the class, no problem. Okay, 2 days it gets a little bit larger, then 3 days it's even larger, and then after 3 days it would be 100% penalty, so we would not accept it. Now that is the stick. The carrot is that we give you late tokens, which can only be used in whole amounts. You can't use a half late token, and you can't use it on a partial assignment. But basically the token gives you 24 hours of extension, no questions asked. Okay? And so in your submission there will be a place to say this is how many late tokens I am using. Also, if you need an extension because of extenuating circumstances, they do happen, especially in a class this large. Almost invariably there's 1 or 2 people whose laptops explode. Sometimes there's other family emergencies or personal emergencies. That happens. People get hit by cars. So you don't have to use tokens in those circumstances. Just talk to the deans or talk to the health center or talk to me, and I'll just say, okay, I'll give you this many days extension, and you can just put that into your submission, and off you go, and you don't lose any tokens that way. Okay. Also, are there seniors in the class? I should see hands because I know there are. And graduate students. Any graduate students? Okay. So this applies to seniors specifically. I want ditch day to be awesome, so seniors get 4 extra tokens. Okay. If ditch day sucks, then I'll take them away. But I want to be able to facilitate a good experience for everyone. And I know seniors work very hard on ditch day, so I'm happy to do that. Okay, any questions? That's that. Assignments, yes. So it is a very time-consuming class. In fact, I don't know why the CS faculty decided it would be good to try to encourage students to take 24 and 38 in the same term, but I think everybody's caught on that that's a terrible idea. So, good luck. But it is a time-consuming class, and I'm sorry, but that's just kind of the nature of systems programming. For a lot of people in this class, this is going to be where you work with the largest code bases you ever have. I'll give you code, you have to understand it, and then you have to write complicated code in a language that doesn't have any safety rails, so you get to drive off the side of the mountain if you want. So you just have to be careful, and so I encourage you to start assignments early for a reason. Usually the first 2 assignments teach people that they should listen to that. And then the 3rd, 4th, and 5th assignments, those are the ones that are really like the hardest assignments in the class. So there's a hump in the middle. Thankfully it's before drop day. Get over the hump, you're probably free and clear. So we want to encourage you to start assignments early, make good use of the teaching assistants, make good use of me, and you'll do pretty well in the class. You shouldn't find it too miserable. Okay? Let me see what else I say here. Yeah, there are some assignments that are more involved than others. I've warned you, so you know, but I'll warn you again. Let's see, and you'll submit your assignments in Moodle. We have a lot of scripts, especially for classes this size. I've been working a lot on automating this class, and so have the TAs. And so there's information about how to package your homework submissions. Please follow that. If you don't, you'll get penalties. But I'm hoping to actually build in an early warning system this year so that if you submit your assignment and it's mismanaged in some way, you'll get an email saying you need to fix this about it. Obviously, if you submit right before the deadline, that's not going to help you. But if you submit early enough, it should help quite a bit. Okay? So that'll help as well. Let's see. Textbook. I have a thing to show you. This is the textbook. It costs $124, so I don't think you should buy it, honestly. It's terrible. Done with that. Okay, so we are using the 3rd edition. The 2nd edition uses 32-bit, and the world has advanced, and just about everybody in here I would expect has a 64-bit processor in your computer, so why not learn to program it? So this is the Carnegie Mellon Introduction to Computing Systems textbook. Bryant and O'Halloran teach a fantastic class, and so they have this book, and it's just great. So if you have $124 to burn, then you can buy it. There's a paperback version of it as well, which I have not personally evaluated, so I don't know if it's any good. Okay. Sometimes you'll see that the different versions of the textbook have different versions of homework problems, and I'm like, why are you doing this to human beings? So what this means is that I will make available, under this country's great fair use laws, I will make available PDFs of certain things that you really need to have from the book, but really you don't need the book itself. If you decide you want to get it, great. I will even, if I'm so motivated, give you optional reading from the book that you can look at if you're curious at what the book says about a particular topic. Okay? But it's definitely not required. Come look at mine in my office if you want. It's a fantastic book, but you really don't need it. Okay? Let's see. Programming languages. So, C, nobody's surprised there, and x86 64 assembly language. Okay, so this is the Intel x86 instruction set that you'll be learning. I do expect that you know something about C. In fact, I think the catalog now says that the CS11 C track is kind of a requirement. It's not something we can really enforce easily. But we expect that you're going to know some stuff about C before you come into this class. If you are thinking that you're going to take the CS11 C track and this at the same time, well, first of all, that's now physically impossible because Mike's not doing CS11 this term. But also, it's just a bad idea because CS24 outpaces CS11 C track by like week 3. So it's kind of a recipe for failure. All right, x86 64, you're not required to know coming in. You can sort of learn it as you go. Now, there is a variation of what students will sometimes do, which is primarily popular among EE students, that they'll already know x86 assembly language of some form, maybe IA32, maybe just the x86, and they'll learn more of the C nuances as they go, and that's certainly an option as well. But you should definitely come into this class knowing something, or else it's going to be really painful. Okay? All right. Let's see. If you, again, get the textbook, you should be aware that it contains a lot of really helpful tips about both C and x86 64 assembly language as we go through. But you know what? The TAs all know C really well. They all did this class, and many of them have done CS124. So they're really clever when it comes to C, and they also know assembly language. But don't expect them to teach you basics of C. I mean, that's not their job. We kind of need you to know that stuff coming into the class. Right. Okay. Any questions about any of this? It's all like stuff you already expected, I'm sure. Now, we have a requirement that assignments must work on 64-bit Linux. People sometimes grouse about this. Why can't I use Cygwin? Well, you might be able to use Cygwin for a few of the assignments. Why can't I use a Mac? Well, you might be able to use a Mac for some of the assignments. But it turns out that there are a whole bunch of annoying technical reasons why we can't design assignments, especially at this level of the system, that work on all of these different platforms. For example, Linux supports both static and dynamic linking of shared libraries. OS X does not. OS X does everything as a shared library, and so calling to even basic things like printf or malloc are a giant pain in the ass. Okay? I won't actually teach you that in this class because it's way beyond the scope of what we want to talk about. Okay? There's facilities that are offered on Linux that are not available on the Mac or under Windows, and so we'd like to use them. And so basically what we do in this class is ask that you either use a CS cluster or the 64-bit Linux virtual machine image that we will provide for you at some unspecified point in the future. Okay? It turns out that assignment 1 is basically all C, so you could do that one on any platform pretty much. You didn't hear me say that, but it is true. We will still grade it on a 64-bit Linux platform. But you know, especially when we get into week 2 and start writing assembly code, you're going to want to be on a 64-bit Linux platform so that you get all of the goodness that is Linux and this kind of environment. Okay? So if you have any other complaints or grousing or issues about that, come talk to me, and I'll tell you many sad stories, and you'll understand. But we do require this because of the level of the system we're working at. Okay? Let's see, GNU tool set. If you happen to be a Clang fan, well, that's fantastic, but you're on your own. We use GCC for C, AS for the assembler, and make for building things, and then GDB for debugging things. Especially that last one. That is going to save you so much time if you will learn how to use it effectively. Okay? I do have supplemental material for these tools. I will make that available this week. It will be in the first week for Moodle. There's a slide deck that I used to use for CS11, and you can read all about it. Okay? I also have a couple of older lectures on using GDB and Valgrind. And you should totally talk to the teaching assistants if you have any questions about these things. I always have students come in and they say, GDB looks too frightening for me to want to sit down and learn it. It looks like it's going to be too much time. I got my assignment due. I'd rather just stare at it or litter my code with printfs or some atrocity like that. And the reality is you want to learn GDB. It will save you so much time. We see people who take 4 hours on assignments and people who take 20 hours on assignments. Well, there can be a lot of differences between those two people, but one of the common ones is that the 4-hour person knows how to use GDB to debug their work. Okay, so you definitely want to learn that. In assignment 3, you'll have to. Okay, but definitely if you learn it earlier, you'll be really happy, and the teaching assistants will be happy to help you with those things. Okay, I do this in the OS class all the time. Students, bleary-eyed and kind of like shaking from fear will come in and say, I have this bug in my OS and I don't know what's going on. And I'll ask them, well, have you figured out how to run this thing under GDB yet? And if they say no, then usually that's the first thing they do, and instantly the bug becomes obvious. And the same is certainly true at this level of systems programming as well. Okay? Let's see. So any questions about any of this? Haven't talked about collab policies, haven't talked about, I'm sure there's other things like, what days to water your plants or whatever other kind of things might appear in course policies, but that'll all be available later this week or maybe today, and you can read all about it and ask me any questions. So I'll certainly send nagging reminders about those things. Okay, motivation. So why should we study this topic? Like, what's the big deal besides the fact that Donnie thinks it's really awesome? Okay. Well, the first one is that if you know how your computer does what it does, then you will be able to use it more effectively. You'll be able to get the most bang for your buck out of this compute hardware. Maybe you can even write exploits like Spectre and Meltdown and be famous. So, but definitely understanding how systems work allows you to use them much more effectively. Now, I have a couple of real-world examples that I've come across, either from friends or from other sources. But I had a friend who was doing a PhD in molecular dynamics, was part of what he was studying for his research. And he was doing a simulation of atoms in 2 dimensions. And so he had to simulate, on really tiny time steps, because I guess you have to if you're talking about atoms. And so he had some number of atoms and a couple of other dimensions to this matrix. And notice he's got 10,000 atoms, and he sent me his code and said it takes a really long time to run, and if I could run it faster, then maybe I could simulate more atoms or simulate with smaller time steps and get better results. And so he sent me code like this. Notice I is 0, I is less than dim, j is 0, j is less than dim, and then he iterated over n. And for whatever reason, that was perfectly fine for his program. Notice he would do some computation for each element. And I sent it back and said, you should reorder the loop like this. Okay, notice I have n on the outside now, and I and j on the inside. And he's like, okay, that doesn't seem like it makes any difference. And computationally, it made 0 difference. The answers were identical. Okay, but the second version ran faster than the first version, and he was thrilled. I think I got like a 3 to 5% performance improvement out of just reordering the loops. Why is that? Well, the answer is simple if you understand how computing systems work. So stick around and you will. Okay. Here's another one. Let's say that the math department decided to be dicks, and they had a candy shop, and they said, we'll sell you candies. The first one is 10 cents, the second one is 20 cents, the third one is 30 cents, and so forth, and you have $1. Okay. So how many candies can you buy? Come on, somebody, this is like hard, Caltech hard math, right? 4, right? It involves arithmetic, so it is hard. For me, anyway, that's why I like computers. So let's say that you didn't know how to do that math, but you did know how to write a C program. And so you wrote the C program to solve the problem for you. Okay? Notice funds left. Okay, I have $1, so I'll just initialize that to 1. I have a for loop that starts at 10 cents and goes up from there, and so price starts at 10 cents. As long as price is no more than the current funds left, then I'll add a candy in and subtract the current price from the funds left. Okay, and then the price goes up by 10 cents. What does this program print? Well, I'm not going to have anybody type it in and give it a run, but you should if you don't believe me. It works in C, it works in C++, and it works in Java. As in, it doesn't work in any of those languages. So if you were to run this, you would see it print out that you have 3 candies that you can purchase and you have 40 cents left over, which seems to be plenty enough to buy the 4th candy, right? Why doesn't that work? Okay. So this is another one of those things that becomes really obvious, and you'll understand after the first assignment why stuff like this happens. You'll also understand why you should never ever compute anything money related with floating point. Okay, and if you do, I will find you and I will wave my finger at you or something. You should not. Okay, so why study computing systems in the first place? Well, these things are easy to understand if you actually understand how the computer does what it does. Okay, you just need a little bit of additional knowledge, and these things become really plain and obvious. Okay. So, and like I say here, we'll see very sophisticated examples as we go through this. It's kind of funny to me because last year, I don't remember it was in a TQFR or in the assignment 5 feedbacks, but somebody was complaining about how caching seems so silly. Why do we care about caching? This is never going to affect me. And then like 2 months later, Spectre, Meltdown, which are cache timing related side channel attacks. And they completely screwed up our operating system implementations. Okay, this stuff is really important. The second reason why we study computing systems is that it turns out that the solutions that people have come up with for these problems are ubiquitous in computing systems. Okay, so it's not like you're going to learn one little thing. I mean, yeah, you're going to learn x86 assembly language, good for you. But it turns out that the basic concepts have been in effect, they've been in use since like the 70s. Okay, so the stuff that you're going to learn in this class is universal. It's the way that we've been solving problems in computing systems for a long time. Very powerful solutions. Totally makes me happy because I have friends who programmed on mainframes. I mean, I think that probably most of you are like maybe in your 20s, but I have friends who were programming mainframes when hard disks were the size of washing machines. And, you know, I came on the scene and started programming stuff and probably used a whole bunch of stuff that's outdated now for you all. But the design principles have been the same all the way along. And to me, that's really awesome because you have these design approaches that have been chosen and they have borne the test of time. They're still in use. They're very powerful. And so it's really helpful to understand these things. So if you ever participate in more advanced system work, okay, which if you take CS124, you will. If you work at any company programming in C or C++, then you probably will. It's important to understand what challenges, what issues are trying to be solved, what are the strengths of various approaches, why is one chosen over another one, and you may even start to realize, hey, there's an even better way to solve some of these problems, and you might be somebody who transforms things yet again. So this stuff is really ubiquitous and universal, and so it's very helpful to know the lay of the land. Okay? Here's an example. We have this process abstraction. In fact, that was kind of the big issue that we ran into with Spectre and Meltdown, is that that abstraction started breaking in certain really serious ways that started to compromise the security of computing systems. Okay? But we'd like to have this process abstraction where one process can't screw up another process or grab information from another process, because you want your web browser that's looking at your online bank information to not have its information leaked into some other program that maybe it's a game that you thought would be fun, but in fact it's stealing all of your information. So you have to be careful about this kind of stuff. The OS needs to provide this kind of abstraction to protect things. Okay? So we'd like to isolate memory used by different processes. We'd also like it so that if one process was poorly written, say your memory allocator, it crashes all the time, you'd like it to not bring down other parts of the OS. Okay? And we also would like to do very clever things with memory management. We'll talk a lot more about this in like week 7 and 8. I don't want to get into it right now. But one of the neat fallout effects of this is that the OS can say there's more memory than there really is. It can overcommit memory because there's a characteristic of program behavior that allows us to overcommit memory. Okay? So it's a virtual memory abstraction. Okay? So the question is, what does the hardware need to provide to make this all possible? And not just possible, but good. Okay? So that's another aspect of things that we'll talk about quite a bit. Okay? So that's just another example of how studying computing systems can help educate you about how a lot of systems go about solving problems, because these thoughts and these approaches are universal. Okay? Okay, next topic, instruction set architecture. So you'll see this acronym ISA. It stands for instruction set architecture, and basically all an instruction set architecture is a set of instructions that you can use to write programs, as well as the data values that they can operate on. And at this level, we're talking really primitive. Like, how do I have a variable? How do I access memory? How do I, input or output to an I/O port to talk to a hardware device? So ISA, we're talking at the processor level. Okay? It turns out that you can have a specification of an instruction set architecture, and then various vendors can implement it, and that certainly has been true of x86 for a long time. Intel and AMD are the two main players right now, but it certainly has not been that way forever. In fact, when I was in high school, there was a company called Cyrix, which made a huge splash in implementing the x86 instruction set architecture and being much faster than Intel. But then they crashed and burned, and I won't go into why. But so that's why you don't know about them anymore. Okay? There are also different kinds of instruction set architectures depending on how you go about designing them. It's kind of interesting. You have one end of the spectrum, which is CISC, Complex Instruction Set Computer. Okay? What we have is instructions that are incredibly powerful. You could expect that there would be an instruction that is, make me breakfast and take the dog for a walk. It's that level of sophistication. I mean, CISC instructions are very powerful and can do a lot of things in one instruction. The reason why CISC exists is because back in the day, people had to write programs in assembly code. Compilers weren't very good, or they didn't exist yet. And so having complex instructions that could do a lot in one instruction made it easier to write programs in fewer steps. The only problem is that if I have a lot of complex instructions, then I need more bytes to encode them. So then each instruction takes more bytes and my programs get large. Okay? But x86-64 is certainly an example of a CISC architecture. In fact, if you look at all of the manuals for x86-64, it's like over 4,000 pages. You got to read that by the first week. No, I'm joking. You don't have to read that. But it is a very helpful reference manual, and you should learn how to understand it because it can be really helpful to understand new instructions. Okay? On the other end of the spectrum is RISC, Reduced Instruction Set Computer. These are a small number of very simple instructions. Okay? And so you need more of them to write a program. These are more appealing if you're a compiler writer because you just have a bunch of little instructions you can chain together. They turn out to be pretty easy to optimize. It turns out in hardware they turn out to be easy to parallelize or pipeline so that I can actually have all of these little instructions going at the same time. So there's benefits and drawbacks. You can see that CISC allows your program to be shorter, but the instructions are larger, so you end up taking a lot of bytes. RISC, the instructions are simpler, so you need more of them, but they're smaller, so you end up with large programs. I mean, it turns out that they're actually about the same as far as binary representation. But you have these various approaches that you can take in designing an instruction set architecture. Okay? Also, a lot of times you'll have a CISC processor like the Intel x86 processor family, and they'll actually take their CISC instructions and they'll have microcode that says what to do for that instruction. And so it might turn that CISC instruction into a series of RISC-like operations that are then pipelined and optimized on the processor level. Again, this is part of the challenge that we have with writing good parallel code and exploits like the ones I mentioned earlier. Okay? So you do sometimes see RISC processors on mobile devices. Like I got my iPhone up here. I bet all of you have smartphones of some kind or other. They're probably all running RISC processors. Okay? A lot of them conform to an instruction set architecture. One of the ARM specifications. Anybody know what ARM stands for? Advanced RISC machines. Oh, there you go. I mean, it turns out that they're easier to implement in a low power way as well. Okay, so how do we build a computer? We're going to actually spend a little bit of time talking about that this week, and actually it's going to spill into Monday as well because we're going to not have class on Friday. But computers are complicated, and it takes a lot of time to learn all of the details about how they work. And so what I want to talk about initially is what are the principles behind the implementation of computers, especially with this whole instruction set architecture kind of approach. So we're going to talk about how they're assembled, and we're going to do a brief tour. Like I say, what are the components you need? It turns out you only need a few components that you can build out of logic gates very easily. What do the instructions look like? Why do they look like what they look like? And how do we implement a computation? We're going to look at those things this week. And so what you find in these kinds of systems, anytime you have a large, complicated problem to solve, is you start with abstractions. You want to break a big problem into a bunch of little ones. And then you want to solve one little problem that moves you toward your goal, and then you solve the next problem in terms of the first problem you solved. And then the next one in terms of the previous one that you solved. So that's an abstraction hierarchy. Okay? We start out with physics. I think physics is cool as a concept, but I don't have time or interest to learn very much physics. So I don't really care about how a logic gate is implemented in silicon. But we do need some physical medium of computation. Okay? We need a way of representing information. And it turns out that you can do this in a whole lot of different ways because the universe has physics, and so there's already computations in effect. And so if we can just figure out those computations and then engineer our own computations using physics, then now we have a computing medium. Okay? And so like I say, we used to use vacuum tubes and relays. You can build a computer out of relays. It'll be very noisy and consume a lot of energy, and it'll be slow as well and susceptible to moths. So you have to be careful about that. You can build computers out of gears. And there have even been computers built out of other things as well. Legos, Tinker Toys, and so forth. Okay? So you get a computing medium. You figure out how to process some unit of information. Typically, being that we're talking about digital computers, we'll talk about bits. And so you have logic gates. And you can construct various logic gates. And then you can assemble those things to do computations. But the nice thing is that once you've gotten to the logic gate level, you stop having to think about physics. Like once we hit that point, I'm like, I'm on board. I don't have to think about physics. I can think about computation. Okay? So then you start building functional units out of your logic gates. It turns out that if you have and not, that's really all you need is and not, you can build arithmetic and logic units. You can do computations. You can build memories. You can build routing circuits, multiplexers and demultiplexers. You can build all the stuff that you need to build a real computer. Okay? And so that means you don't have to think about logic gates anymore. Turns out I haven't thought about and not, well, until this morning when I looked at my lecture. Okay? So from those units, you can build a programmable computer. And we're not going to talk about it today, but next time you'll see how one can assemble these components to build a programmable computer. It's a very powerful concept built from simpler concepts. Okay? So, like I say here, You'll notice this right away. Like assignment 2, you're writing assembly code and you're saying this is pretty lame. And in assignment 3, you're debugging assembly code and you'll be saying this is really lame, Donnie, and so forth. And so what you want to do is keep extending this abstraction hierarchy so that you can start doing more powerful things without having to think about all the other junk that's going on under the hood. And so we get runtime support, like a stack for function calls, so that I can reuse units of computation. Okay? I want to have some place that I can dynamically allocate memory for when I want to use memory in ways that doesn't work well with function calls. Okay? A lot of details like that. So we'll talk about some of the basic runtime support that we need. We'll talk about that next week for building programs. Okay? And then you start getting into operating system facilities. Like, boy, wouldn't it be neat if I could store data and then later on, like after my program is terminated or after the computer's been turned off and on, I can still get that data. Or I want to do stuff with another process so that we're sharing a CPU. Okay? Very common approach. And you can go on and on. There's just so many abstractions that are built on top of this basic hierarchy of abstractions. Okay, any questions? Very, very powerful stuff. And you'll see that. Well, through the first 4 weeks, we're going to go through a whirlwind tour of the basic facilities that are leveraged by programs all the way up to, let's say, Java and Python. Okay, so you'll see how we build all of these things, and you'll know how they work from logic gates up, which is pretty dang neat. Okay, so we are talking about digital computers. We're talking about binary digital computers, not trinary, which is confusing and scary. So, but at this level, we have zeros and ones. Okay? Everybody is familiar with zeros and ones. And so logic gates are going to allow us to process zeros and ones to make more zeros and ones that hopefully mean something for us. And so here are a few examples, again, that I expect you're all familiar with. We have an AND gate, which only produces 1 if all the inputs are 1. You can see that this is a truth table, and down at the bottom, the D with the inputs and the output, that's how you draw an AND gate if you were so inclined. Okay? Here's an OR gate. You can see it's kind of maybe a D moving at high speed or something. It's got a little bit more of a slant to it. But OR gate produces 1 if any of its inputs are 1. So it only produces 0 if the inputs are all 0. And here's a NOT gate. NOT gate is really obvious. The input is 1, I output 0. And if the input is 0, the output is 1. Okay? Now we can construct really sophisticated systems just from logic gates, it turns out. It turns out that you can even build OR from AND and NOT. So that's why we really kind of only care about AND and NOT. And if you look at a lot of different chip designs and so forth, they'll talk about NAND gates, not AND. And so you can build a lot of stuff out of just NAND gates. And so that's a very common approach. But A or B is just, remember, we produce 0 only if all the inputs are 0. So we can invert our inputs so that we only produce 1 when both inputs are 0. And then we can invert that and we have an implementation of OR. Okay. Here's another one, exclusive OR. Exclusive OR basically tells you if there are an odd number of bits on your inputs. Okay. So we produce 1 if only one of the inputs is 1. In this particular case, 2 input XOR. So we can design that easily out of AND, OR, and NOT. Okay. Anybody can figure that one out. That's not too difficult. And of course, we know that we could take that OR and also turn it into ANDs and NOTs. So you could end up, again, building everything out of ANDs and NOTs. But once you have something like exclusive OR, you don't have to think about ANDs and NOTs and all that junk anymore. How do I make this out of ANDs and NOTs? Or how do I make this out of physics? We don't like physics in this class. So, you can see that you can build up these abstractions, and then you can use those to do computations. And so that allows you to stop thinking about some of the details you may not want to have to mess with. Okay? Now, it turns out that with AND, OR, NOT, and exclusive OR, you can build arithmetic. You can do addition and subtraction, and I'll include some supplemental material on Moodle showing you how to do addition and subtraction very easily using just these logic gates. Okay? But we have some problems we need to solve. we need to figure out how are we going to represent values with bits, because we're really good at computing with zeros and ones right now. But what if we want to do a 2 or a 3? Then we're screwed, right? We have to come up with a way of representing those things. Okay? And so we need to be able to do that. This is all part of the data representation issue or question. Okay? How do we represent values? And you could ask that in a broad range of contexts. How do I represent text data? How do I represent floating point numbers or fixed point numbers or arbitrary precision numbers, which are frightening? You know, so there's all these things that you could represent, and you would have to design a data representation for some of those things, unless there's already a common one in use. Like floating point was crazy. Back in the 70s, there wasn't like one way that people did it. And so different processors would get different answers with the same math. So somebody said, we need to standardize this, and this guy came, really clever guy came up with a way of doing it, and we all agreed to do it that way, and now we're better off. Okay? You still can't do money with it, but that's okay. At least you can do science with it at least. So anyway, we have to come up with a data representation. So we'll talk about unsigned integers, just to illustrate. Okay? We're used to writing numbers of 0 through 9. Probably comes from having 10 of these things that we can wiggle. And so each digit is 0 to 9. So what we'll do for our data representation on our computer is we'll just represent digits, or let's say numbers, as a sequence of these bits. Okay, vector of bits, where each digit is a 0 or a 1. For the sake of simplicity, we'll also constrain ourselves to a certain number of bits total, be it 4, or in our case 64 for x86 64. We'll say we have this many bits to represent values. That'll be our default size, and that will allow us to do computations efficiently with values of that size. Okay? So we map a particular vector of bits to its corresponding unsigned integer with a calculation like this. You know, we're all familiar with the ones place, the tens place, the hundreds place, the thousands place. Well, in binary, we have the ones place, the twos place, the fours place, the eights place, the 16s place, and so forth. Okay, it's the same thing, it's just a different base. Okay? And so you'll see that the bits are numbered 0 to w minus 1, w being the bit width. Okay? 0 is the least significant bit, so that'll be 0 or 1, and then the next bit over will be 0 or 2, and so forth, all the way up. Okay? So this is how you would represent 42, everyone's favorite number. Okay? So we have this, and if you were to expand it out, so 0 times 2 to the 0, 1 times 2 to the 1, so that'll be a 2, and then 0 times 2 squared, 1 times 2 cubed, that's 8, so we have 2 and 8 is 10, and then we have 1 times 2 to the 5, which is 32, and everybody should know that 32 plus 10 is 42. Yay, we're done. Right? So that's how you do 42 in base 2 arithmetic. Okay? Now adding is just as straightforward. We just, we do it in columns or in places, just like we do, long addition. Everybody's familiar with doing that from the distant past. So, and just like in base 10, you have a carry. You have a carry out that you have to think about. Okay? Fortunately, it's just a 0 or a 1, so that makes it nice and simple. Okay? So if we want to add 106 and 105, I just got like a mild panic attack because I think somebody found an error in one of my lecture slides. So be on the lookout. If you can find an error, then let me know. But anyway, 106 plus 105. Now we can all eyeball this and say, oh, that's going to be 211. So that's fine. But we can also just do this in base 2 and go through and say the initial carry-in is 0. 0 plus 1 is 1. That's fine. Carry the 0. 1 plus 0 is 1. Carry the 0. Okay, 1 plus 1 is 10, because we're in base 2. So we have a 0 and carry the 1. That one's easy. 1 plus 1 is 10 again, but now we have 1 plus 1 plus 1 is 11, right? So this problem definitely goes up to 11. And so you carry the 1, and you end up with this result. Okay. And if you were to, again, multiply all that out and add it up, then you would get 211. You get the appropriate answer. Okay? Easy peasy. Now, all we need to do is figure out how to implement this in logic gates. And you might eyeball that. This is the truth table for what we like to do. A, 1 bit of A, and 1 bit of B, 1 bit of carry in, and then that'll produce a sum and a carry out. Okay? And if you were to reverse sum and carry out, you'd see that it makes total sense, because only one input would be a sum of 1 and a carry out of 0. If you have 2 inputs, then the sum is, well, the answer is 10, so we have 0 with a carry out of 1. And if you have 3 inputs that are 1, then the answer is 11, and so that would be the last example. Sum is 1 and carry out is 1. Okay? So this is where you have to build the machinery, and it's gross, and nobody really wants to do that. So I'm going to kind of skip over this part. The sum is always 1 if we have an odd number of inputs being 1. Right? So exclusive OR is our friend in this case. We can just throw a bunch of exclusive ORs at it, and we get that, no problem there. Carry is kind of a pain in the ass, so again, I'm not going to talk about it very much, but you can certainly look at that and see that carry in is going to be 1. Carry out will be 1 as long as we have at least 2 inputs that are 1. Okay, so that's what we're computing here. Now, who wants to think about that when you're doing addition? I don't. So we abstract it away. We build this thing called an adder. We actually call it a full adder because it adds A, B, and carry in. And it turns out that you can build a full adder from 2 half adders that take care of A and B and then incorporate carry in. Okay? That's the slow way to do binary arithmetic. There's much faster ways, but it's a nice straightforward way. Once we have this box that adds junk, then we can just stamp that thing out, and we can add large, numbers of bits together very easily. So notice we have something that does the 1's place, and then that's something that does the 2's place, and does the 4's place, and the 8's place, and the 16's place. We do our carry out. This thing is called a ripple adder. It turns out that it's pretty dang slow, so we don't do math this way on processors, but it's easy to understand, and so it's a great illustration of how you build a computational system from physics, really, is what we're talking about, building it from physics. Okay, any questions? All right, so that gives you an idea of how this all works. Now, one important detail that we need to pay attention to is that for a certain bit width, we can only represent certain values. And you'll notice that given our mapping of the bit vector to a value, we can really only represent integers from 0 up to 2 to the w minus 1. That's the best we can do. Like if all our bits are 1, that's what we can calculate out. So you learn these numbers as you do systems programming. 8 bits, I can do 0 to 255. 16 bits, 0 to 65,535. And you just sort of learn them and memorize them as you go. Okay? So what happens if we add 175 and 114? Do we get a value larger than 255? Yes, so we're sad. Well, maybe, our computer's not sad, but we certainly are. Because if you did this, you would get a value that requires more than 8 bits. And so we know the answer should be 289, but the computer says the answer is 33, and we're really sad. Okay? So, ideally the computer tells us that there was a problem. Worst case, your multi-million-dollar spaceship blows up. Things like that happen. You irradiate people with too much radiation and they die. Okay? These are things that have happened. So, sad, right? These kind of systems can fail in these ways. Okay? So here's the question. Can the computer tell us there was a problem? Yeah, we have a C out up at the top. If that thing turns out 1, we should freak out. Probably a little bit, right? Because we know our answer is incorrect. Okay? So we can label that overflow. Hooray! Okay? And so now when we have an overflow, we can detect that there was a problem. Okay? So we call these things status values. There are a whole bunch of different status values. Okay? But yeah, we can definitely write computations that look at these status values so that we can do the right thing if an error occurs. Okay? Now, we have a little bit more to talk about. We may go a few minutes over time, and I just ask you to bear with me because That was unsigned arithmetic. We need to also be able to do signed arithmetic because negative numbers are a thing. And so we need a way of representing signed values as well. And so this is the most common representation. It's called 2's complement. Basically what we do is we take that topmost bit. Remember, that was the 128th place if we're talking about 8-bit numbers. And we're going to say the most significant bit is going to use us to either start at 0 or shift us over to like the most negative we could possibly go. Okay, so you can see that the topmost bit, x sub w minus 1, is now inverted. We have a negative sign in front of it. We'll subtract that from our answer, and then all the less significant bits will be added in. Okay? So that topmost bit, when the topmost bit is 0, it's a positive number. When the topmost bit is 1, it's a negative number. So we call it the sign bit, right? That's a big shock, but we call it the sign bit. So, again, with W bits, we can only represent a certain range of values. Minus 2 to the W minus 1, that's if the topmost bit is 1, and all the other bits are 0. So we're shifting over to minus whatever, and not adding anything to it. Or we can go all the way up to 2 to the W minus 1, minus 1. That's if the sign bit is 0, and all the other bits are 1. We're adding as much as we can and not subtracting anything. So, for example, with 8 bits, you would end up with minus 128 to plus 127. And it has this nice benefit that 0 is right in the middle. Okay? All right, let's look at this really quickly. I want to give you a quick introduction to this stuff. There is an easy trick, which I have to say I actually learned from Glenn George when I was an undergrad. So, easy trick for inverting an integer into 2's complement. Okay? You invert all the bits and then add 1. That's all it is. Okay? So 2's complement for minus 42. We already know what it is for plus 42 because we saw that earlier. So we invert the bits, and then we add 1. Okay? Easy peasy. And so if you were to do that through our 2's complement conversion, minus 1 times 2 to the 7, so that's minus 128 we're adding in, and then we add in all the other components. You do the math, you end up with minus 42. So hooray. But that's 2's complement integer representations. Okay? Now, the overflow rules have to change for this. And this is one of those things that you would notice immediately if you decided that you wanted to compute minus 1 plus 1. Well, what's minus 1? 1, 1, 1, 1, 1, 1, 1. If that was 8 ones, that's minus 1. Then you add 1 to it, and we know that we get an overflow. Okay? So we add 1 to that. What's the uppermost carry out? Well, it's a 1. Does that mean that we have an error in our computation? Not this time. And so this is one of the interesting things about these things is that how you identify overflow with signed arithmetic is different from how you identify overflow with unsigned arithmetic. We're not going to talk about it. Don't worry. Okay? But what we end up doing is that little overflow thing that we had a couple slides ago, we change its name. We say it's unsigned overflow because signed overflow needs to be computed in a slightly different way. Okay? Really only care, well, I'm not even going to go into it. Just read up about it. I don't want to even get sidetracked into it. Any questions? Okay. So, summary. We have a data representation. Hooray! And we know how to do signed numbers and unsigned numbers. So next time we're going to start talking about how to implement various processor components, what they do, and how to hook them together. And so make sure you take care of these action items. I would say probably the most important one to start now is your CS cluster account if you intend to use it. Second most important is get enrolled on the Moodle. Okay? So we'll see you next time.